Okay, perfect. So thank you everyone for being here. It's something I've been working on for a couple of weeks, maybe a month or two. But this is something I had in the back of my head for a long time because it's used in many contexts. How can we use and how can we overcome the limitation of Bayesian model selection? So the title of the talk is Separating Epistemic and Aleatory Uncertainty Using Conditional Bayesian Model Selection. This is what I propose as an alternative to the standard Bayesian model selection. So first, why do we care about that model selection in the first place? So there are two key applications that in my mind are worthy of being interested in that topic. First is that if we have two models, model A and model B, we want to answer the question, which one of those two best explain the data? Okay, so that can happen all the time. We were facing this problem earlier this year with Dye and Barkov, where we had BDLM versus LSTM. We were working on that benchmark competition for predicting dam behavior. Which model works best? Okay, we were having a really hard time when trying to use Bayesian model selection to figure out how can we quantify probabilistically which of those models works best, or at least best explain the data. The second one is when we want to do ensembling. Okay, we want to have several models and we want to combine the prediction from those models in order to improve prediction accuracy. But again, we face the same problem. When we try to use Bayesian model selection to assign weights to each model in terms of probabilities, what Bayesian model selection tends to do is to concentrate the probability on a single model. So what I'm going to present today is first a review of what is mathematically Bayesian model selection. So first, a little hint, this is the classic formula for what is Bayesian model selection. We're going to go through it. And we're going to go through what are the current limitations associated with it. Then what I propose as an alternative is what I call conditional Bayesian model selection, how it works, what are the possibility, and how it compares quantitatively with Bayesian model selection on case studies. And finally, what I'm going to tell you is that conditional BMS, I think it's only a trick. I think it's a decent one, but it's not the real thing. I think the real thing is because we missed something in that formulation. And we're going to look at this in terms of what future work we could do and looking at the covariance induced by input variables in regression problems. So I'm going to start with Bayesian model selection. This is the classic approach we use when we want to compare models. So let's take the context where we have M models. So G is my model. The subscript M refer to the model index. All these models share the same input variables as well as sets of parameters. Okay, and we want to compare these M models where each of them is going to be associated with the observation model that takes this form. So Y's are the observations, G of M is my model, and VM here are aleatory errors. Okay, in this case, for now, we can assume homoscedastic aleatory errors, IIDs across all observations. And we have this observation models across M different models. So let's assume that we have a set of data consisting of tuples, xi, yi. So x are the input variables, y's are the observations. And we have this for d tuples. So what we want to obtain as a final answer is what is the posterior PMF for each model, so 1 to m, given the data. And the classic Bayesian formulation to obtain that posterior probability is what is the likelihood of the data given the model times the probability of the model divided by, this is simply a normalization constant over all the possible models. So if we want to simplify this, because we want to remove the prior, it doesn't really play a role here. We want to assume that the probability of model is 1 over m, so that we can remove it from our equation, not because prior is not important, it's because here it doesn't play a key role. This is not what we want to look at for now. So let's assume it's a uniform prior over all models, so we can just remove it from our mind and have a simpler equation. So in that case, it's the likelihood of my mth model at explaining the data divided by the sum of the likelihood of all my models. And in that case, what is that likelihood of data given the models? That corresponds to the denominator, the evidence from my classic Bayes formula for my parameters. So the posterior PDF for my parameters given the data for a specific model M is the likelihood of the data given the parameters times prior for parameters divided by that evidence, that normalization constant. And this is what is used in that Bayesian model selection formula. Typically, for general classes of problem, this is crazy hard to obtain. However, for special classes of problem, Gaussian process regression with state space model, linear state space model with TGI, all this is tractable. Okay, so whenever we're Gaussian linear, this we can handle it. So in our case, since we deal with state space model and TGI with Bayesian neural nets, we have access to this, but still we're going to have a hard time with this. I'm going to explain why. And any of you, as usual, feel free to stop me, ask question, ask clarification, ask me to slow down at any point or accelerate. Okay, feel free. So we're going to look at our first example of comparison between two models taken from state space model to analyze time series. Okay, this model has two simple components. The first one is a local level. So local level is just that constant baseline that we want to infer. The second one is a periodic component to model something that is a sine-like signal over time. So my observation model, Y, is the baseline component plus the periodic component plus an observation error VT, which is an IID error process with zero mean and variance sigma v squared. Okay, classic business as usual. So what I'm going to do to test the capacity of Bayesian model selection, I'm going to say, I'm going to generate data with that periodic component, having a sine period of 365 days. Okay, but in reality, when we want to compare model, no model is an exact representation of the reality. So what I want is to compare that data that was generated with that 365 days with models that were not generated with 365 days as a period. So model 1 is 363, model 2 is 367. Okay, so in your opinion, what should be the probability of model 1? And what should be the probability of model 2?
I mean, you picked a number exactly in between, no?
Yeah, on purpose. So what should be the probability?
Purpose,
what do you think should be the probability of each of those models at explaining the data?
I would say like it's kind of like we have the unidentifiability problem because it's like both sides, you know?
So what probability?
I think 50-50.
50-50.
50-50,
you agree with this?
Yeah, 0.5, yeah.
0.5, right? There's no reason to think that it's symmetric. Okay, they're going to be equally marginally bad on each side. They're not exactly it, but
that's true.
None of them should be better than the other. Okay, so it means that Bayesian model selection should give us 50-50. So let's try it. So the bottom figure you see here is the real data. Okay, the blue is the real data. And if we analyze the data with a period of 365 days, you see in red, we have the real baseline, in black, the expected value, in green, pale green, the confidence region. Okay, we have the same thing. The red is the real periodic component. The black is the estimated value. The confidence region has just vanished. It's so small. What we have on the second line is model 2. You see that it's really still very good at extracting the real baseline and really good at extracting the real periodic component. Same thing for model 1. Okay, so if we use Bayesian model selection, what would be the probability of model 1? 95, model 2, 5%. Okay, so all the way to associate with 363 period, 363 days period. Okay, what if I generate, I use the same setup, but just generate a second synthetic data set? What would happen? I generate a second synthetic data set. Now we have the same kind of qualitative result, but now the probability of model 2 is 93 and probability of model 1 is 7%. So whenever I change the data set, it's either one or the other model, and it always flips. And if I do this a lot of time, I did it 1,000 times. And what you see here is an histogram of the probability of model 1. What we see is that most of the time it's either 1 or 0. It's never 0.5 or almost never 0.5. It always go, I'm sure it's model 1 or I'm sure it's model 2. Instead of saying, I don't know, it's 0.5. Both are equally good or equally bad. Okay, and this showcase one of the problem we're facing when trying to use Bayesian model selection. It tends to concentrate all the probability on a single model. Okay, and that probability is not reliable in the sense where if you change the data, you're going to completely flip your probability to another model. So to summarize the issue with Bayesian model selection, the posterior PMF typically wrongfully concentrate the probability on a single model, as I showed you. And the second issue is that that probability greatly varies across data set. So either probability of model 1 is going to be much greater than model 2 or vice versa. And for each new data set, that probability flips. So my hypothesis to explain this is that the root cause for these limitations, the last two, are the same. It's because we include the aleatory uncertainties in the likelihood calculations. Okay, so what happened is that the variability in the likelihood values induced by the aleatory uncertainty. So this is my noise process. That is my sigma v square zero mean observation error process, will tend to dominate the difference in the likelihood between models. So the change in likelihood caused by my aleatory error process cause more change in my global likelihood than the difference in my two models. So the difference between a period of 363 days or 367 days. And this issue tends to grow as we have more data. Okay, the more data we have, the more these issues are exacerbated. Okay, the more we see the probability content concentrate on one single model. So in order to overcome these limitations I was perceiving when trying to use Bayesian model selection, I've been to propose that conditional Bayesian model selection. Okay, what is the idea? Is to separate the epistemic and aleatory uncertainties when we do the likelihood calculation. Okay, so the epistemic uncertainty, just to remind you, is the uncertainty associated with the parameters or the hidden states in the model. Those uncertainties that should shrink to zero as the amount of data goes to infinity. Okay, and the aleatory uncertainty comes from your error process, whether it's observation errors or prediction errors. Okay, but those that are not associated with hidden states or parameters. So in that case, that conditional posterior PDF of my model, conditional on aleatory errors. So my aleatory errors are my vectors of error process for each of my observations in Y, is going to be given by my probability mass function for M, given D, but also given realization of my aleatory error process. Okay, so in that case, I have my conditional likelihood divided, if I assume that, again, that I have my 1 over M prior over all the models, so I can discard it because it's not relevant for now, divided by my normalization constant, which is the sum of that conditional likelihood over all my models. This is what I have on my denominator. So if we look at this with the eyes of the previous example, we'll look on state-space model where I have the sum of my baseline component, a periodic, and my process error. So it means that my conditional likelihood here, f of y given a realization of the error and a model, is going to be distributed like the sum of two random variables, the one associated with my baseline, the one with my periodic component, but VT now is not a random variable anymore. Okay, it's a scalar, because now I want to make it conditional on the realization of my error process. So now that conditional likelihood is going to be, in the case of state-space model, a normal, is going to describe the probability of predicting YT given a mean and a variance. So given this is my model, the mean is going to be the sum of my level component plus the mean of my periodic component plus VT, which is a scalar. And my variance is simply going to be the sum of the variance of the level plus the periodic component. Okay. So in that case, if I want to obtain my probability of model conditional on my aleatory uncertainty, my joint likelihood for my observation is going to simply be the marginal product of the likelihood for each observation. I'm going to take the product over my t time steps, because this is a problem with time series, divided by the same thing, the sum of the same thing over all my model n's. Okay. So we can obtain the joint posterior for both, because this was just a conditional. So conditional probability of model given my aleatory error. Now what I still want to consider these aleatory errors because I don't have access right now to V. Okay, I don't know what are my observation or prediction errors. So I need to consider them probabilistically. Even if I didn't consider them though, I have access to that conditional probability of model given my errors, but I don't have my errors. So what I need to do, I need to obtain my joint, the joint for the probability of model and my aleatory errors. So to do this, since I have my conditional, I just multiply by my marginal probability of errors, where my marginal probability of errors is going to be my observation process. Okay, mean zero, covariance, sigma v. So then if we want to remove that error process from the joint, I need to marginalize. So integrate over all possible V's for my model VM. So I'm going to have a PM tilde given data. Okay, and this is not exactly the same as what I had before with Bayesian model selection, because Bayesian model selection will include the aleatory error in this calculation. Whereas my conditional, I explicitly take them out. So I take them out before calculating that marginal or that conditional probability of model. So as I said, these two, the tilde, the conditional probability, conditional Bayesian model selection is not equal to the formula of Bayesian model selection, because Bayesian model selection will have include these aleatory errors in the likelihood calculation, whereas I explicitly got them out and then weight each of the outcome of likelihood by the observation error process. Okay, so okay, but whenever we see stuff with integral, usually we don't like. Okay, stuff with integral is not fun. However, in practical implementation, in our case with state space model or KGI, this is roughly trivial to obtain. Why? Because to obtain that integral here with respect to my prior, actually, we can just do that very quickly and very efficiently with sampling. So we just do 1 over S, the number of sample I take, the probability I calculate for my conditional probability of model given my error process, where this instance here, I don't know it. So what I do, I just sample from my prior knowledge from the error process. This is a normal with mean zero, variance, sigma b squared. I take samples in there. I take a sample VS, replace it here, compute this sum over all possible samples. So in terms of implementation, this is trivial. This is really, really simple to apply when we want to compare models. At least when we have Gaussian equations like this one, this is super easy to do. So this is the same equation as we saw before for the formulation, for the marginal likelihood, conditional likelihood of observation given my observation errors. So if we want to compute or express explicitly what is going to be my posterior conditional, my posterior PMF for the model given the data, the one that is conditional, is going to be 1 over S, number of sample, the sum over all my sample. On the numerator, I'm going to have my joint conditional likelihood divided by the same thing where I normalize over all my model M. Where in this case, all the VMs you see here are actually a sample from my observation error, draw from a zero mean Gaussian. Okay, so this is trivial to implement in practice for Gaussian models such as GPR, state space model, and Bayesian neural net with TGR. Okay, so let's take this full example we had before with these two components, level and periodic. We again have our real data that is, or synthetic data that is generated with a period of 365 days. My two models, 363, 367. As we said before, we expect a probability of model 1 of 0.5. Okay, so here we have an example. Again, another comparison. So the truth here is the third line, model 1 first line, model 2 second line. So what you can see is that the first column here, model Bayesian model selection has a probability of 0.16 for model 1, 0.84 for model 2. Not so great. Conditional Bayesian model selection, 0.49, 0.51. Okay, so we had a 0.5, 0.5 we were looking for. Again, I repeat 1,000 times. This is what we have. Bayesian model selection is what we have in blue, the same as I presented before. Conditional Bayesian model selection is the curve in red here. So you see that it goes around that 0.5. We still have variability, but it's pretty narrow around that 0.5 value, which means I don't know whether it's 363 or 367. And it doesn't oscillate like crazy from one data set to another. It always stays around that probability of 0.5. That is consistent with that symmetry that I built in that counter example to show that there were some issues with Bayesian model selection. Okay, so that was a first example. So now let's look what happened if we apply this to Bayesian neural networks, okay, using KGI. So the first set of example is for model comparison. Okay, I have different models. I want Bayesian model selection or conditional Bayesian selection to tell me which one of these models is better than others. Okay, so I have this toy regression problem. The reality is that black line, it's x cubed, okay, x cubed plus v. I'm going to analyze this model with a simple feed-forward neural net, one hidden layer, one output layer, that regression problem. And I'm going to have, one output layer. I'm going to have one hidden layer, which contain a variable number a of hidden units. So the number of hidden units, I went from 10 different models, where model from 1 to 10 have 2 to the power m number of hidden units. So my model 1 will have 2, model 2 will have 4, 8, 16, 32, like this. Okay, and I want to see among these 10 different configurations, which one should have the best model? Oh, which one best explain the data? Okay, I want to use model selection to tell me this, assign a probability to each of those 10 models. So first, before looking at what are the numerical results, which one of these two models is better? Left or right?
Left.
Left is better?
Yeah, I think left as well.
Yeah,
But
everyone
right
kind
is
of
more
agree.
there.
So here we would expect that Bayesian model selection and conditional Bayesian model selection should tell us that the model to the left is better than model to the right. Okay, this is pretty obvious. So we don't need a metric for this. Okay, we visually see this is right. So to tell you, the model on the left is this model 6 with 64 hidden units for the hidden layer. The model on the right is model 4, 16 hidden units. Okay, second test, which model is better? It's harder, huh? So anyone want to guess a probability?
50-50.
It's not far from 50-50, huh? So in this case, if we look at the numbers, left is again 64 hidden units, right is 1024. So left is M6, right is M10. So what we would want for Bayesian model selection or conditional Bayesian selection is to give us a probability that is close to 0.5 for these, or at least not necessarily 0.5, but roughly equal probability for these two. Okay, so let's look at the comparative. So I have my 10 models here. So model 1 is 2 hidden units, 4, 8, 16, etc. And the 10 is 1024. Okay, in blue we have Bayesian model selection, in red conditional Bayesian model selection. So Bayesian model selection to tell me that model 6 has 90% of the probability weight. Model 10 has 0. Okay, this is one of the issue. Okay, on the other end, if we look at conditional Bayesian model selection, we see that model 10 is twice as likely as model 6, but it's not clear cut which one really dominates the other. And if we want to make prediction, we still need to consider both, because both still have a meaningful or really substantial probability content associated with them. Okay, so that was the first example with model comparison. So we really have 10 different models. We want to compare the performance of each of them. Now we want to do a second task of model assembly. We're going to have 10 almost identical models. We want to know how should we combine each of them. Okay, so to do this in a neural net, it's easy because each of them is going to have the same number of hidden units, 100. However, in neural nets, whenever you're going to start with a different initial seed for your parameter, you're going to end up with a slightly different model that's going to give you slightly different prediction. Okay, we want to know which one of these initial seed is going to be better, and we want to assign a probability to each of these different initial seed. So again, we'll see. Okay, so model 3, model 6. So both have 100 hidden units because the 10 models now have 100 hidden units. What differentiate them is the different initial seeds. Okay, so what's the probability for model left and right? 50-50, huh? I wouldn't say I bet against any of those two models. Okay, if I wouldn't need to make a prediction, I would say trust those. For me, they are almost identical. So now we have a probability of like 97 for model 3 for Bayesian model selection. Okay, and again, if I would repeat this exercise many times, it would never always be model tree. It would change from a model to another one. Whereas with conditional model selection, model tree is a little better than the other, but it only carries about 23% of the weight. Some models that were less good, like model 2 or model 5, are indeed ranked lower, or slightly, but they still have comparable weights as expected up front because the architecture and everything is very similar. Okay, we just have slightly better initial seed than others, but certainly not, I wouldn't say that model tree carry 95% of the predictive power that we have here. Okay, so all this looks nice, but I think I just found a good trick. I don't think this is the real thing. Okay, I think everything is right with the real Bayesian model selection. I just think that we don't use it properly. And using it properly is way harder than we currently do. Okay, and this has to do with prediction error dependency. Okay, so let's look at the problem where we have again that toy regression problem. The black is the reality, the red is my expected value, and the green region is my confidence region for my predictions. Okay, so what do we see here is that we don't model exactly the reality. Okay, at some place we deviate from this reality. And the issue we have is typically when we do our problem, we don't consider prediction errors. We only consider observation errors, and that is problematic. Okay, so typically we don't have that W term. Okay, we're going to say Y equal G of X and theta plus V, the observation error, but we don't have an explicit terms to account for prediction errors. Okay, and prediction errors and observation error are not exchangeable. They're not the same. What is specific with prediction error is that prediction errors are covariate dependent. Okay, we can see that for a different location X, I'm going to have fully dependent prediction errors. So for instance, if we look at here, coordinate xi and another coordinate xj, the error I have there and the error I have there are going to be strongly positively correlated. Okay, if I take two slides that are very close apart, if I know the error at one location, the error at the other location is going to be very similar. Okay, and the more I get away, the more that correlation goes away. But still, and if we take any pair of slides across this covariate region, I can find a dependency structure. And if I don't include that dependency structure, that covariance structure of my problem in my likelihood calculation, I'm just completely off. And that's what leads to these my hypothesis is that that's what leads to these completely random shift in the probability assignment to every model. And that also leads to the concentration of the probability content to single models. So the issue is now, how do we model that covariance between the prediction errors as a function of the different covariate xi and xj? So with AGVI that Barkov presented in his thesis, we can model heteroscedastic variance. Okay, the variance of my prediction errors dependent on a given xi. But now it's not the variance I want, it's the covariance. Okay, all the off diagonal terms, but that's not for multiple prediction. I have a single output y, but I want the dependency across the different value x I want to predict in my validation set I want to use for performing my Bayesian model selection. Okay, so with AGVI, we can extend it to model that covariance that is input dependent. Okay, so how do we do this? So business as usual is this framework. Okay, so here from the previous architecture I showed you before, I just represent use the compact notation where that vector Z1 is one hidden layer containing, say, 100 hidden units. Okay, I have my Z output, I have my error term V, zero mean normal with variance sigma V square, and Y equals Z output plus V. Okay, this doesn't work. This is what we've tested already. Now what I'm telling you is that we need to add V, explicitly my error process. And what Barkov did in his thesis, it showed how we can directly do this with neural net by having heteroscedastic variance. Okay, but heteroscedastic variance is not enough because it won't consider the correlation or covariance between different prediction errors. So what we can do with our existing formulation with AGVI is to extract for any xi or xj what is the posterior for WI? What is the posterior for WJ? Okay, given the data we've observed, we can have a posterior estimate for both of these quantity at any location. So we can again take advantage of the fact that the covariance between WI and WJ is the expected value of WI times WJ. Why? Because W is a zero mean process, okay, or zero mean random variable. So the covariance is the expectation of the product of the two variable, WI, WJ. So now what we can do is that we can have a two input neural net that will model this, meaning that the top branch of my neural net is a feed-forward neural network that takes as input Xi. The bottom branch is a feed-forward neural network that takes as input Xj. So this is a hidden layer of, say, 100 hidden units. This is a second hidden layer of 100 hidden units. And these two hidden layers combine into a single output, WI, WJ bar, which is equivalent to the expected value of WI, WJ, which is that covariance we're looking for. Okay, and we learned this network through observing different instances. For given Xi and Xj, we can obtain these two values. We multiply them together. We can use this imperfect observation as an observation or information here to update this value for the expected value of WI, WJ. And here you see I have some arrows with equal. Why? It's because all the weights and bias in that first layer between my input and my first hidden layer are shared across the two branch. And here's the same. All the weights and bias I have here and there are shared across my two branch. Why that sharing? It's because this network must work in a symmetric way. If I switch Xi and Xj, if I permute the order, I should still obtain exactly that same expected value. Okay, by sharing the same way top and bottom branch, I'm sure that if I flip Xi and Xj, I'm always going to get the same value. If I use Xi, what I have here is going to be the variance. Okay, so I can extract all the terms from this network of a full covariance matrix. Okay, so if I have a bunch of terms in my validation set, I want to query. What I do for all Xi and Xj in my validation set, I query my neural net here with any pair of Xi, Xj, and build my full covariance matrix for my validation set. Okay, I put it with an at. Why? Because this matrix is not going to be PSD. As soon as you try to build a large scale covariance matrix from pairwise definition, it's always going to fail. Okay, so we need to solve this. How do we solve this? We're going to assume a prior on a lower triangular diagonal matrix, lower triangular matrix. Okay, L prime. I'm going to assign a broad prior into any term of that random matrix. Then I know if I take L primes times L prime transpose, I'm going to have a prior for covariance matrix, which is again going to be a broad prior, but it's going to be fully PSD. Then what I do, I use this matrix, which is not PSD, as an observation to infer the posterior for L double prime. And if I do L double prime times L double prime transpose, I'm going to have a covariance matrix, which is going to be guaranteed to be PSD. Okay, so I'm going to be able to retrieve the full covariance matrix for my validation set. And thus, I hope, this is again future work, I hope I'm going to be able to obtain good result with Bayesian model selection. And I won't need to use conditional Bayesian model selection because now I'm going to take into account the fact that my prediction errors are dependent across my input variables. So as a conclusion, Bayesian model selection, as I've shown you, has several issues related to overconfidence about a single model. So it's really going to concentrate all the probability mass on a single model, and that model will change from data set to data set. So my hypothesis for this is that the root cause is the inclusion of wrongly considered aleatory uncertainties in the likelihood calculation. So conditional Bayesian model selection that I've proposed here seems to mitigate the overconfidence issue. However, I'm pretty sure it's not the theoretically correct solution. Bayesian model selection is right. I think it's the way we use Bayesian model selection that is not. So again, my hypothesis for this is that the real issue is that we neglect the covariance between prediction errors. That's it. Questions, comments?
So far, you haven't tested the last bit.
Nope, nope. This is what I was trying to explain to you on the board the other day, but I
Yeah.
didn't have time to implement it or test this last part. This is just a hypothesis and gut feeling.
Very nice.
James?
Yep.
I mean, like, this whole part is crazy, but do you think this is scalable?
I mean, yes and no, in a sense where it depends. The answer is it depends. Of course, if you deal with very large dimension, you're gonna
Yes.
have very high number of dependency terms. But on the other hand, it doesn't depend on that much on the dimensionality as it depends on how much your data vary across those dimensions. So imagine that I have a flat plane in a million dimension. This is going to be very easy to learn. If I have a function that varies like crazy in a million dimension, that's going to be hard. But even a function that varies like crazy in 2 dimensions is crazy hard. So it depends how much that kind of dependency structure, how complex is that dependency structure in space. My intuition is that it's going to be pretty complex. So
I mean,
go ahead.
I mean, anyways, we won't be able to see that, right? You have to test for all possible combinations of I and J.
You don't necessarily have to test for all of them, but if you don't use them, you're leaving information on the table. You can use as much as you can, and if your real covariance is 0 is a flat plane, you don't need to test a million of them. You're going to find pretty soon that you learned that it's a flat plane everywhere. Whereas if it's super complex, you're going to see that the more pairs you see, the more you improve your covariance model.
Because if you have like multiple features, like just take a small, like the small UCI dataset where, for example, housing dataset has, I think, 12 or 13 features, having total of, I don't know, some 500 points. So imagine doing it between features.
But it's not between features, it's between vector of observations. So if you have 1,000 data points in your training set, you're gonna have to choose tuples of 2 among the set of 1,000 observations. So all possible combination of 2 observations in your set of 1,000 observations.
So all features together in one, and
yes,
all
because
features.
it's always a vector you observe. You cannot separate the vector.
Okay.
However, you might need a lot of data to learn all this complexity of dependency. So maybe that in 25 dimension, 1,000 data point might not be enough to give you a good model of your covariance across that gigantic domain. But right now, no one investigated this, so we don't know.
Okay, I see. It's the same problem with if I have like 40 points and I want to learn a heteroscedastic variance, just the regular one. I cannot, just because the points are not enough. So it's the same problem, but between data points. Okay, see, thank you.
So were you guys able to follow most of it? I know maybe I went far and I went quick on some aspect.
No, it was on the spot.
It's interesting because like after our discussion, I worked at this a bit on this like on my own just to play around with it. And your conditional BMS, I had something quite similar, but I hadn't thought of the prediction error as a potential explanation as well. I don't know enough about neural networks to.
But my feeling is that this is not specific to neural net. I explain it with neural net because it's super easy for me to test with it, but you can take any model and it's the same. So even linear regression. So if the polynomial you're using is x squared and you're trying to fit x cubed, you're going to have dependency. And in practice, you're never going to have the right polynomial order to fit exactly what you want. You're always going to end up with dependency in your prediction errors. And at the end, if your process is dependent and you assume an independent process to measure the likelihood, you're going to be super strongly penalized. Whereas if you're linearly dependent between your prediction errors, it counts as one error. It doesn't count like 1,000 errors. Whereas if you assume that they're independent, you're going to be penalized for each one of them. And that just kill one model versus the other. This is a feeling. I haven't tested it fully yet, but this is, I think.
No, but it makes sense. But like, I'm just thinking, like, even in actuarial models, like if you predict, let's say for a gamma variable and one of your predictors is paid claims and you're trying to project like ultimate amounts. Well, if you have a gamma with a fat tail, obviously like the prediction error will just like exponentially increase. So it will be correlated.
Yeah. And I think considering these correlation error is crazy hard. So this is one of the reasons why few people tackle it, because here in a simple model, we can use like a Gaussian kernel to model a kind of a covariance structure, but it's going to work on a really limited region for a simple 1D case. As soon as you want to generalize this in multivariate case, these kernels are just going to fail miserably because they're going to be just locally good. Globally, they're not going to be good. So that's why here I found that it could be interesting, because with neural net, we can have a lot of capacity to generate covariant structure that are not like hard-coded function that could really be driven by the data themselves. And to say that, for instance, these closed value here should be positively correlated, these domain here should be positively correlated, but this one and this one should be negatively correlated. Okay, and this is already a trivial, simple problem, and we need to handle all this. A Gaussian kernel cannot handle this. Okay, how do we do this? I think neural net in this way could be a way to tackle it. I haven't tested it, so I cannot really say it works yet, but this is going to be a next thing to test those things.
James, and regarding the symmetry problem that you were talking the same day you were explaining to Ali, will it work in this setup, or there is still some work to be done?
I haven't tested it. I don't know. I'm having some
theoretically, you think?
I'm having some.
Sorry?
I'm having some wishful thinking here. I hope it's going to work.
Okay.
But I have no guarantee, because it requires kind of special feature where these two, I'm not worried. Okay, so going from here to there with the same way, it's going to work. It's kind of the same hidden layer evaluated with two different inputs. But now we need that we see two different vector of hidden units, and with the same set of weight from the two sets, we predict a single output. I've never tried it. I've never seen anyone try something like this. So I'm not sure yet if it's going to work. But if we want to model covariance matrix, we need this, because otherwise we're not going to have the symmetry. And as soon as we're going to go in large dimension, we're going to have problems. And by enforcing that symmetry, by the symmetry in the weights, in the top and bottom branch, we should solve that symmetry issue. And I'm pretty sure from what we saw with your work on AGVI for the multivariate process, with this trick, we're going to be able to enforce that positive semi-definiteness of our covariance matrix predict with our neural net. You don't seem so sure.
We'll see.
Oh, but you can express it. I mean, I haven't tested it, so everything is possible.
Yeah, I mean, there is always issues. This is what I've learned.
Because my idea was really to do exactly like you did. You assume a prior on L prime, very broad prior, multiply it. This is going to be PSD. This is not. But this gives you information, very precise information about what should be all of your covariance term. This is going to be, you're going to have directly a covariance between L and this. So that's going to allow you to directly infer L double prime. L double prime by itself should give you a PSD covariance matrix. This is the idea. Still remain to be tested.
Mm-hmm. Seems like a good idea. If it works.
If it works. So that's it. Other questions, comments? I feel that I've lost you guys in the details.
James, so from the result that you saw, for a neural network with different seeds and different architectures, the weights for each model, it's like really different.
Yeah.
But the weights for different model with different seeds, the weight are kind of the same, right?
Yeah.
So this is different initial seeds, right?
Yeah, each of the
So the
models is
weights-
the initial seed.
Yeah, so the weight is kind of similar.
Yeah.
Yeah, so I was, am I correct that if I just do ensembling based on the different seeds,
Yeah.
I just use equal
I mean,
weights?
you can. It's not a bad prior, but I think using these weights is going to be better because, for instance, model 3 is still maybe 10 times better than model 4. So when you're, imagine you want to ensemble a 100 or 1,000 model, there are going to be some seeds that are going to lead to catastrophically bad results. There are some seeds that don't converge or get stuck, or it can happen all the time. And if you don't check them manually, you can include in your sum a model that is really, really bad. So with this, you can really see still, okay, model 4 and model 2 should be still weighted down compared to model 3 and model 8. So of course, using a uniform prior should still lead to something that is reasonable, but this, I haven't tested it, should lead to something that is better than averaging.
At the cost of computation, right? At the
But the
computation
cost of computation is fair for computing the weight. The cost of computation is almost zero. So the cost of computing the cost of training 10 different models is order of magnitude more expensive than calculating the weights. Calculating the weights is almost free. So it's really the training of
Okay.
each model that is expensive. The
Okay,
calculating the weights is really negligible.
okay.
The problem is right now is and this is the same thing we face when we use that benchmark model where we had 10 different seeds for the LSTM. We were trying to use Bayesian model selection and we were always getting something like this. All the weights was giving on a single model, and we decided not to use it because we didn't see any reason why this model should be better than the others. So the problem right now is not that it's too expensive to compute those weights, is the weight we compute kind of make no sense.
Okay, thank you, Jim.
James?
Yep.
Here the seed is to generate the initial value for the parameters, or
Sorry,
generate-
repeat that.
the seed, what is the seed used for?
Basically, it's because whenever you want to use TGI or any neural net, actually, you need to randomly initialize all your weights and bias to a given value. And every time you initialize with a different initial value, you end up with a different set of weights and bias. You're not going to end up at the same place. So every time I randomly generated the initial value for weight and biases, so that at the end, each model make a slightly different prediction.
Okay, so the seed here is to generate the initial value for the parameters. And these different models, they have the same structures, but start from different points.
Exactly. And this is what's done in deep ensemble, for instance.
Thank you.
And Sebastian, just to clarify, you were saying that this is especially true.
Something that I tried, so I was testing to see if obtaining the conditional would give, or the marginal would give me the same as just using cross-validation. But it's, if you have to train your model, the moment it's a little bit complex and you sample each time with a different seed and you have to retrain, like it slows it down considerably.
Yeah.
So this was a comment from like what you were saying, calculating the weights is free, but training the models is slow.
Yeah, definitely.
And James, what did inspire this? Was it the IQL benchmark inspired this whole research?
Initially, yes. I think what gives it the push, yes, because we were using it, we were faced with it. the Bayesian model selection formulation is really simple. We know it, it's known for ages, but it's also known for ages. No one uses it because it never works. And it's kind of unclear. I couldn't find any place in the literature that really tells me why it doesn't work. Everyone knows it's this, but why it doesn't work, it's kind of unclear. And when we were trying to use it, it was giving exactly the same issues I was showing here, concentrating all the, either when we were comparing two different models, putting all the weight on a single model, even if the prediction leaps seems pretty fair for the two models. And at the end, when we were trying to ensemble, only one model would give a significant weights, 0 for everything else. And we tried to figure out, do we have a bug? Do we do something? We checked it a million times, everything was right, and it was still not working. So I got this in my mind last winter. And at some point I had a kind of a light bulb moment. Oh, maybe this is the issue. And when I kind of kicked in with what was the issue, it was the last seminar, when I told you about that kind of likelihood variability across data set. And this is why I kick, okay, aleatory uncertainties play a role that is not taken care of in the current formulation. So I should investigate this. And this is where I came with that conditional Bayesian model selection. But again, I think this is just a fix. I don't think that this conditional Bayesian model selection is the real thing. It's just a nice trick, but since it's a trick, I don't yet know when it's going to fail. I think the Bayesian model selection is the real thing, but we're not using it correctly.
Thanks.
So last chance for a question. Yeah, go ahead, Sharon.
Yeah, I have a question. Like I think on slide like 4 or 5, the one that you explained the equation for the SSM. Yeah, there you go. That's it. I mean, this model selection that varies from, let's say, jumping from 90% from one model to another one. Is it sensitive to that sigma v? So what I mean is that if the sigma v is very small.
Yeah, I'm pretty
And
sure
then-
there's sensitivity all over the place to sigma v and very high sensitivity to the number of data.
Okay. Because I assume that if sigma v is also 0, so we don't have any
No problem.
observation noise, so no problem.
Yeah.
So the moment that sigma v introduced, then it's going to create a problem.
Yes,
And
but
it
I
doesn't
don't
matter
think
whether
it plays around in all. I think there might be also regime where if it gets really, really high, it doesn't pose problem neither. I think it's it's not the monotonic problem where it's just always increasing as you're increasing.
on and off. Okay.
Because if you put sigma v to infinite and your signal is drawn into noise, this is just going to be 2 clouds of noise. So it's again something different. So there's a kind of, I think there are multiple regime in there. I haven't investigated enough to really give you a clear-cut answer there. Just that it's not straightforward.
No, that sounds like promising because if it works, because one of the I think one of the major issues in neural net, I mean, is like selecting like the architecture of the number of units, number of and everyone does it based on experience, trial and error. There is no let's
But
say
it's the same
systematic
thing
solution.
here. You still need to, it doesn't drive, you still have to test all the combination you want to compare. It just gives you the probabilistic way of quantifying the weight you should assign to each of those architecture. And hopefully without concentration all the weights on a single one.
Because I mean, yeah, that's true.
No more questions? Melina? No questions?
All good.
So that's gonna be all for the seminar this week. We're gonna get the last seminar of the season next week. Second.
Yep.